Hey everybody. This is supplement 2 for week 3. We're just covering one minor topic that we didn't quite get through in Wednesday's class, differentiability of functions of several variables. Uh, Looking at this definition of differentiability, which is also closely related to the idea of local linearity. Okay, so we had talked quite a bit about partial derivatives. We have a definition here for differentiability, which is slightly different. You might think that, in a sense, partial derivatives are just the only derivatives or something like that, but we'll actually see throughout chapter 14 that we have ideas like directional derivatives and so on. So this idea of differentiability is a bit more general than we've discussed so far. So definition. We say that a function of two variables, z equals f of xy, is differentiable, or in other words, that it's locally linear at a point AB if delta z, which we define to be f of a plus delta x, b plus delta y, minus f of ab. So this is the change in the output if we vary both the x coordinate and the y coordinate at the same time. If this delta z can be expressed in the form delta z equals fx delta x plus fy delta y. So like our linear approximation, plus two other terms, epsilon 1 times delta x plus epsilon 2 times delta y, where specifically epsilon 1 and epsilon 2 both go to 0 as delta x delta y goes to 0, 0. We have a theorem related to differentiability, which is quite important because it's typically not easy to show differentiability directly from the definition, but the theorem says that if the x and y partials both exist near a point AB and both partials are continuous at AB, then f is differentiable at AB. So typically, this is how we're going to show that most functions are differentiable, showing the partials are continuous. But let's take a look quickly at the definition of differentiability. Okay, so this was example 4 from the lecture. So if you wanted to slot this into the lecture, that's where it would go between examples 3 and 5. So example 4, prove that f of xy equals x squared plus y squared is differentiable using both the definition of differentiability and the theorem up here. Okay, so the theorem is fairly easy to use because in this case, fx equals 2x, fy equals 2y. Both partials are continuous on all of R2. So therefore, by our theorem, f is differentiable on R2. Okay, but let's try to show this using the definition of differentiability. So what do we need to show? We need to show that delta z equals, again up here, f of a plus delta x, b plus delta y. So f of a plus delta x, b plus delta y, minus f of a b. We need to rewrite this as this little increment from the linear approximation formula plus some other stuff and show that that stuff satisfies these criteria, epsilon 1 and epsilon 2 going to 0 as delta x delta y goes to 0, 0. Okay, so what is f of a plus delta x, b plus delta y? This is a plus delta x squared plus b plus delta y squared. And then minus f of ab is minus a squared minus b squared. We can multiply everything out, get a squared plus 2a delta x plus delta x all squared plus b squared plus 2b delta y plus delta y squared minus a squared minus b squared. We see the a squareds and the b squareds cancel out. And furthermore, we see from up here that fx at a comma b equals 2a, and fy at a comma b equals 2b. So this equals, well, 2a delta x is fx delta x. 2b delta y is plus fy delta y. So that's these two terms. And everything that's left over has to get wrapped into these epsilon terms. So we want a plus epsilon 1 delta x. Well, the only delta x's I have left over are the delta x squared. So I'm going to write this as delta x times delta x. And same with the delta y squared. That's the only delta y that I have left over after taking care of those two other terms. So plus delta y times delta y. And again, to match these up to what we set up here, we take epsilon 1 to be delta x, epsilon 2 to be delta y. And these both go to 0 as delta x delta y goes to 0, 0. So because I was able to write delta z as this linear increment plus epsilon 1 delta x plus epsilon 2 delta y, where epsilon 1 and epsilon 2 go to 0 as delta x delta y goes to 0, 0. Because of that, f is differentiable at ab for any arbitrary point ab in R2. So we've shown directly using the definition now that f is differentiable on the whole plane. But obviously it was much easier, even in this fairly simple case, to use the theorem to show this, to show that the two partials exist and are continuous. And then as a little aside, here we're going to focus on the 1D case. We're going to show that f is locally linear at x equals a. In other words, the 1D equivalent of this definition for differentiability, which is sometimes referred to as local linearity instead of differentiability. We'll show that f is locally linear at x equals a if and only if f is differentiable at a, that is, f prime of a exists. So what we want to do is we want to show that we can find an m such that limit delta x goes to 0 of f of a plus delta x minus f of a minus m delta x all over delta x. We want to show that that limit equals 0. That's essentially what this criterion says, but in one dimension. We want to show that that limit is 0 if and only if f prime of a exists. Well, let's start by going left to right. So let's assume that this limit with the minus m delta x up here is 0. Now we do have to decide what we want to pick m to be. What would be a sensible thing to pick m to be? Well, I noticed that this first bit of the numerator, if I just wrote that and kind of forgot for a second about the m delta x term, well, this is just f prime of a. So I'm thinking that m is going to end up being f prime of a. I do notice that if I put minus m delta x on here, I can split this into two fractions, minus m delta x over delta x. And of course, the delta x's divide out. Keep in mind, delta x is going to 0, delta x is not 0, so we can safely divide those out, and we just get a minus m. So we'll assume that this limit equals 0. However, the limit of the difference is the difference of the limits. So this says that limit delta x goes to 0, f of a plus delta x minus f of a over delta x. And of course, limit x goes to 0 of the constant m is just m. We can add that to the other side. This limit exists and is equal to m. And of course, we recognize this limit as f prime of a. So if the limit up here, the original limit, equals 0, so if the limit exists and equals 0, then f prime of a exists. Then this limit must also exist. What if we go the other way? Suppose f prime of a exists. Then we'll take m equals f prime of a, and we have limit delta x goes to 0 of f of a plus delta x minus f of a over delta x, and then minus f prime of a delta x in the numerator. Now, what do I know about this limit? F prime of a exists, so it's a real number. I have the limit of the difference of two fractions is the difference of the limits. And again, I can make this minus f prime of a delta x over delta x, or just minus f prime of a. F prime of a is a constant in terms of delta x. And we, of course, see because f prime of a exists, this limit is just f prime of a. So the original limit must be 0. So we've shown that this original limit equals 0 if and only if f prime of a exists, if and only if f is differentiable at a. So the ideas of locally linear and differentiability are essentially equivalent, at least in the cases that we're discussing. Okay, so that's actually all for the supplement. So again, not a big supplement today, just a little technical detail here. That wraps up the material for 14.1 through 14.4 for this week. And next week we'll start on 14.5 and move on from there.